Have you ever stopped to think about the secret language that's running behind, well, basically every app and website you use? It's the reason some things feel lightning fast and others just don't. Today, we're going to pull back that curtain and take a look at this language: data structures and algorithms.
Really think about it for a second. How is it that your phone can search through thousands of your contacts in a split second, but some other app takes forever just to load your feed? The answer, and this is the cool part, isn't just about having a faster phone. It's about something way, way smarter happening under the hood. You'd think that with computers getting faster every single year, being efficient would matter less and less, right? Well, it's actually the complete opposite. This quote from Virginia Tech just nails it. We don't use all that new computing power to just do the old stuff faster. Oh no, we use it to tackle these massive, complex problems we couldn't even have dreamed of solving before.
And this chart right here really shows the race we're in. That bar on the left, that's our computing power. And yeah, it's growing at a nice, steady pace. But then you look at the bar on the right, that's the complexity of the problems we're trying to solve, and it is just exploding. It's growing exponentially. And that giant gap between them, that's what we have to close with smart software.
So the big question is, how on earth do we bridge that gap? If we can't just throw faster hardware at the problem, what's the secret? How do we build software that can handle all this growing complexity without just grinding to a total halt?
Well, the answer really comes down to two fundamental ideas. On one hand, you have organization, which is all about how you store your data. We call these data structures. And on the other hand, you have process, the actual step-by-step instructions for what to do with that data. And those we call algorithms.
But here's the thing. For any combination of data structures and algorithms you pick, there's always one single question that is more important than any other. Just how efficient is it? Because it's not enough for a program to just get the right answer. It has to get it in a reasonable amount of time, especially when you're dealing with massive amounts of data. So let's start with data structures. Before a computer can do anything useful with information, that information has to be organized in a logical way. Think about it. You wouldn't just dump all the files on your computer into one giant messy folder, right? Of course not. The exact same principle applies here.
Now, before we jump into some cool examples, we need to get this one key idea down. It's called an abstract data type, or ADT. It sounds kind of academic, but the concept is actually super simple. An ADT is just a blueprint. It defines what you can do with your data, not how it's actually done. Think of it like a TV remote. The volume up button makes the sound louder. You don't need to know anything about the wiring or the infrared signals inside. You just know what it does. That separation is an absolute superpower in programming.
Okay, so let's take a simple idea, like a list. One way to build it is something called a linked list. The best way to picture it is like a line of people all holding hands. If you want to add a new person right in the middle, they just have to grab the hands of their new neighbors. That's it. Nobody else in the line has to shuffle around or move. This structure is fantastic when you need to add or remove things all the time.
But what if your data isn't just a simple, straight line? What if it has some kind of hierarchy? Well, for that, you'd probably use a tree. Think of a family tree, or even the folder structure on your computer. Everything starts from a single root, and then it branches out into parents and children. It's the perfect way to organize anything with those kinds of relationships.
And then, for the most complex, interconnected stuff, we have the graph. Just picture a subway map. Any station can connect to any other station, and there can be tons of different paths to get from one to another. This is the exact structure that powers things like social networks, GPS directions, and, the entire internet.
Okay, so our data is all organized and neat. Now what? Well, now we need the recipe to actually do something with it. And that's exactly what an algorithm is. It's like a perfect recipe from a cookbook, a clear, specific, finite set of steps that takes you from your ingredients to a delicious, finished dish.
And for something to be a true algorithm, it has to follow a few simple but very important rules. First, it's got to be a function. That just means if you put the same inputs in, you will get the exact same output every single time, no surprises. Second, it has to be unambiguous. Every step has to be crystal clear.
And third, and this is crucial, it has to be finite. It actually has to finish at some point.
So, what does an algorithm really do? Well, let's take one of the most common jobs out there, sorting. On the left, you see a jumbled mess of numbers, total chaos. A sorting algorithm is the recipe that's applied to turn that mess into the perfectly ordered list you see on the right. Looks simple, right? But how it gets from chaos to order is everything.
So, we've got our data structure, and we've got our algorithm. But how do we know if our recipe is any good? Is it a 5-star recipe, or is it going to burn the kitchen down? How can we measure its performance in a standard way, a way that works on any computer? For that, we need a special kind of language.
I mean, just for a single problem like sorting, there are dozens of different algorithms. Some are really simple to write, others are super complex. How in the world can we compare them to figure out which one is the best for the job? We can't just time them with a stopwatch, right? The result would be different depending on your computer, the programming language, even the data you feed it. We need a better way.
And this is the exact problem that Big O notation was invented to solve. Now, don't get scared by the formal math definition on the screen. The core idea is actually incredibly simple. Big O doesn't measure time in seconds, it measures growth. It answers the question, if I double the amount of data I have, does the work I have to do double, or does it quadruple, or does it get way, way worse? It's all about predicting how an algorithm is going to behave when things get really big.
And this gives us a fantastic way to rank how efficient things are. At the very top, you have O of 1, or constant time. This is the dream, the holy grail. It takes the same amount of time no matter how much data you throw at it. A little further down, O of n, linear time. That makes sense. Double the data, you double the work. But look what happens toward the bottom. O of n squared, quadratic time. Now if you double the data, the work quadruples. And that last one, O of 2 to the n, yeah, that's a complete meltdown. An algorithm like that becomes totally useless with even a pretty small number of items.
Okay, this isn't just a bunch of abstract theory. These concepts, these data structures and algorithms, they are powering the technology you are using every single second of every day. Let's make this real. You know when your GPS finds you the fastest route to get somewhere? That's not magic. It's modeling the entire road network as a graph, where cities and intersections are the points and roads are the lines connecting them. Then it runs a shortest path algorithm, like the famous Dijkstra's algorithm, to find the absolute most efficient way to get you from point A to point B.
And what about that social media feed you were just scrolling through? That is a massive, massive sorting problem. There's an incredibly efficient algorithm running in the background, sifting through millions of posts to decide in a fraction of a second what's most relevant to show you next.
And searching for a contact on your phone? It feels instant for a reason. Your contacts are sorted alphabetically. So instead of checking every single name one by one, which would be O of n, your phone uses something called binary search. It jumps to the middle of your contacts, sees if the name is before or after that point, and instantly gets rid of half of the list. It does it again and again and finds any name in a huge list in just a handful of steps. That is the incredible power of an O log n algorithm.
So there you have it. Data structures give us organization, algorithms give us the process, and Big O notation gives us the language to measure efficiency. These are the fundamental building blocks that let us turn seemingly impossible problems into the seamless technology we use every day. You now know the basics of this secret language, so the only question left is, what are you going to build with it?